Hello and welcome to the first installment of our Building Automation webinar series. This four-part series from Element 14 in Texas Instruments will discuss key subsystem blocks for fire safety, building security, and HVAC systems. Today we'll be discussing the connected sensing with Miro from Texas Instruments. If you have any questions for Miro, please use the Q&A window available through the WebEx function. If you have any technical issues you can't hear or see, feel free to mention me directly through the chat window at Premier Farnell Webinars. A recording of this presentation will be made available after the conclusion of today's presentation. So without further ado, I'd like to turn it over to Miro, who's going to walk us through today's presentation. Miro?
Hi, thank you, Dave. So my name is Miro, and I'm working in TI in Industrial System Group, specifically focusing on building optimization. So today we are going to talk about energy efficiency in building optimization, solution using innovative wireless sensing, and also predictive maintenance. So why we are talking about connectivity and building optimization and everything today, we have a buzzword that is called Internet of the Things, IoT, better known. And what is IoT? IoT is basically connection devices, vehicles, buildings, and other items enabled with electronic software, sensors, and other network connectivity that enables these objects to connect and collect data and exchange this data. It is predicted that we will have around 50 billion objects connected by 2020. That's a lot of connectivity to be made to that point. So first thing, when we are talking about connectivity, connectivity makes sense if we have sensors, and TI plays a big role in different sensing area. We can see temperature. We have temperature sensors that are used in connectivity and sensing, power measurements, current shunt measurements, magnetics, proximity, Hall effect, inductive capacity, ultrasonics. You have maybe touch screen or elevators. They have push buttons or something. That's all proximity sensing, PR motions, and so on. Lighting, occupancy detection, gas fluids, biosensing, positioning, material pressure, and so on, so on. So these sensors are extremely important, and that's where we are starting, because when we have Internet of Things, we want to connect a physical process to the cloud, and we want to have access to that one. So what is the first building block? That is a sensor. So here is example of the sensor node. So on the left side, you can see that we have a sensor. Now, in this case, it's a Wilson bridge, normally used for the pressure sensing. In the middle, there is analog front end, which needs to process that signal coming from the sensor, filter it, and gain it. And also, we have a power supply and gain control. So that's all in the middle portion of the analog example of the sensor node. On the right side, where is wireless node, we have a power management. We have a microcontroller with application specific software. We have RF core and antenna for further communication. So TI's presence in building optimization is also committed through something called TI designs. TI designs are example of designs that we do for different very specific applications. So for example, here you can see specific room which can be connected to the cloud, and we have daylight harvesting, we have a gas detector, automated window blinds, voice speech recognition, thermostats, smart plugs, glass break detectors. We have also automated ceiling fans designs, motion detectors, and so on, so on. All that is connected naturally to the gateway. So what are these TI designs? TI designs are basically these reference designs when we gave example of component selection, PCB realization. There is a board, physical board. There is a software associated with that one, and they are all test results, so that someone who is interested, for example, in motion detector can look for the PIDI 00489, for example, and see how it's done, and based on that one, starts its own design. So first thing that when we are talking about these sensor nodes is how we are going to supply them, and power supply. Now, if we are going to have a wall power supply that limits the range of the sensor where we can position it, and it's not always practical, so we always start from the battery. And in a sensor nodes, battery efficiency is the key. That is a key of the design. So we have here wireless connectivity, for example, 2.4 gigahertz, and we are going to look for sub 1 gigahertz connection, and that will determine energy requirements from energy source or from the battery. Normally, we target 10 years battery life. And why 10 years? Because battery manufacturers cannot guarantee more than 10 years of the shelf life of the battery, so there's no point making a device that can run longer than the source. And so we are trying to design our analog and wireless design around 10 years battery life. So now in some situations, for example, when we have BLE, then we cannot use small batteries, or batteries by itself cannot supply enough energy, so we need to do additional harvesting, energy harvesting, to supplement the battery and extend its life. So solar harvesting naturally is the most commonly used, but there are also other sources like thermoelectric generation or vibration and so on. So also we are going to see two different types of the sensor nodes that they are going to be always on, analog, always all, or interrupt-driven for different applications. So let's look immediately on wireless connectivity power requirements. For example, here we have sub 1 gigahertz. On the left side table there is sub gigahertz compared to BLE. Two different TI parts, the CC1310 and CC2650. Requirements are different for these two parts. So for this example, we are going to look sub 1 gigahertz example, and we will say that one event transmission length of the position is 104 milliseconds, and standby is for 60 seconds. Now we need also to be very careful. All these calculations are not entirely correct, and that's okay. So why I'm presenting that one? It's not correct because it will depend of how you're doing encoding and how many bits or bytes you're transmitting. So this is example from our TI design, and these are very specific results. So 10 events. If we have 10 events per hour, we can calculate the current. We can see when the radio wakes up and transmits how much current we are transmitting. So average current that we need from the battery is 0.6 microamps. So now if we have a coin cell battery, and coin cell battery has 220 milliamps hours at 3 volts, and in 10 years we have 87,000 hours, we can calculate with efficiency factor of 0.85 that basically that battery can provide us an average of 2.1 microamps. That's quite a little current, it's a low current that we need to deal with that one. But we just saw that wireless connectivity that we calculated in sub-gigahertz domain, the average current is 0.6 microamps that we need to provide. So for our analog and digital signal path, we are left with 1.5 microamps. So our circuit needs to operate on less than 1.5 microamps so that we can guarantee 10 years on a coin cell battery. Different story is if we are using AA batteries. AA battery is 2,700 milliamps hours, which is almost 10 times more. And so that's on 1.5 volts. So if we put 2 of them, we will have 3 volts as in the previous example. And we can see that now we can have 26 microamps average power. So depends of the size, depends of the application. If we are going with coin cell, we have 1.5 microamps to design our circuit. If we are going with AA batteries, we will have around 25, less than 25 microamps to design our circuit and to operate that one. So that is for sub-gigahertz. The problem arises when we are going with BLE beacon, for example, and we are assuming here that BLE beacon is transmitting once a second. In addition, we have a heartbeat LED diode that blinks every 2 seconds for 100 milliseconds, so equivalent to 50 milliseconds blink per second, you know, if you're looking for the duty cycle. And on right side, we can see the requirements. You know, we can see how much current we have for wake up, pre-processing, receiving, transmitting, processing, LED blinking, and sleep mode. So that's all on 3.1 volts voltage, and we can calculate required power, and also we have a time in milliseconds, how long are these durations. We said that it's happening once per second, so we can see that total sum of the time is 1,000 milliseconds. Automatically, we can see the energy, microwatt seconds, what is necessary for this BLE beacon, and we can see that it's 186 microwatt seconds. Now, using a TI part, CC 2541 from TI Design 1000, we can see that to obtain that kind of energy, we are using the solar panel that at 250 lux will generate 200 microwatts. So that is equivalent of the energy that we will need for beacon, and we can see that our current, required current, is in the range of 60 microamps. We just saw in the previous two calculations that our sub-gigahertz is going to consume 0.6 microamps, so that is 100 times more for BLE beacon. So if we are going to go with BLE beacon, we cannot run it easily on battery for 10 years, or lifetime needs to be shortened, or we need to have additional energy source to supplement these requirements. So how we are going to do that? We can see here that there are different energy sources that can be used. One is solar panels, that's mostly used. We can see that we can have 10 to 10 kilo microwatts per centimeter square, and that depends on the type of the solar panel that we are using. Then there are thermoelectric generators, there is vibration, and there is also our RF power harvesting. So all that will come as a supplementary energy source to the power management circuit. And here we can see that in the power management circuit we have a primary source, which is normally non-rechargeable battery, you know, or backup battery. And then we have a secondary source, which is rechargeable capacitor bank. So we can see here, for example, we are using BQ 25504, that's TI part, and that part will manage, you know, energy source, will manage primary source and secondary source, capacitor bank, basically, to provide now energy to the load. And what is the load? Load is a sensor, analog to and digital signal parts, microcontroller, and the radio. So here are different types of solar cells for energy harvesting, and on the left side we can see for different applications we have indoor, outdoor, and also the wide range. It's specified by wavelength in nanometers, and also we can see the conversion efficiency of the solar cells that then are used to create a solar panels, solar modules and solar panels. And so nominal voltage on the single cell will be around 300 millivolts. Open circuit is considered double of that, that's 600, and maximum power voltage will be around 500 millivolts. Now, it's very important to say that BQ part that we were mentioning before can do maximum power point tracking, and we can see on the graph that there is a maximum power, depends on the voltage that we are applying and depends on how much light we are shining on a single cell. So let's talk about energy harvesting process and BQ part 25505 from Texas Instruments. We can see here that there is on the left side there is a solar cell, then there is a boost converter, you know, we have a capacitor block, and then we have a secondary charge capacitor. First thing what will happen is a cold start. Cold start will happen when our capacitor is under 1.8 volts. So solar cell will start to trickle the current through the boost converter. Basically, it will not work as a boost converter. It will just go through the main switch. You can see with the red arrows how the energy is going, and the cold start will just permit that energy to transfer to the capacitor and to charge the capacitor up to 1.8 volt. And you can see on the graph on the right side that the cold start starts very slowly. You know, we are going to turn on the MOSFET, then the voltage is going to jump and continue rising as the solar cell is providing energy. And once when we arrive to 1.8 volt, then BQ will start a normal operation. In the normal operation, the energy, the boost converter now will operate as a normal boost converter. We'll take a low voltage from the solar cell, we'll boost that one, and we'll charge the main capacitor, storage capacitor, and also will charge a secondary storage capacitor bank. So that voltage will keep rising, and at one point when it arrives to the 3.2 volts, it will switch to the next level and will turn on the load. We can see that the load will connect around 3 volts, 3.2 volts, but what will happen at that point, the voltage will drop down because now we have a load that is attached to the capacitors, will take energy from the capacitor and voltage will drop. So we can adjust this hysteresis. In this case, it's 2.9 volts, and the part will continue working. This is case when we don't have a primary source connected as a backup battery. So it's only working from the solar cells. Another way of harvesting energy, which is very common in a water heater, is using thermoelectric generators. So on thermoelectric generators, we need to have heat on one side, and we need to have a cold on other side. Means we put the ice cube here in this case just to show, but bottom line is we need to create a difference in the temperature between two plates. And so the water heater is perfect example of that one, because we always have one side that is heated and we have another side that is not heated. So pilot flame with a thermoelectric generator is common way to use it in this kind of application. Now, before we were talking about different requirements and different systems, how we are going to design. And so I will start with a very simple example. Let's say that we have two sensor nodes. One will be temperature sensor node, thermostat. Let's say that we are just measuring temperature in a room, and another one will be motion detector. So for the thermostat, we need to measure the temperature. And we normally measure temperature once per minute, let's say once per minute, because temperature is not going to change drastically in a range of milliseconds, or nothing is going to happen very quickly. There is a thermal inertia, and we really don't care what's happening between two measurements, because we know that the change can be very slow between these two measurements every second, for example. So in this case, you can see on the right side the block diagram where we have a power management, and we have a nanotimer that is going to control the load switch. So the nanotimer will be programmed that every second, for example, will close the load switch and will provide a power from the battery to the sensor and to wireless block. So in the sense of the interrupt. So we can see, on the diagram here that in a first period, standby state, radio is hibernate, analog front-end monitor is waiting for interrupt to send that one. And so now during the interrupt, when the nanopower system provides the power, then the sensor will wake up, wireless will wake up, and we will measure the temperature and we will transmit that one. Now, there is another case where we cannot do that one. For example, if we have, the motion detector, we cannot go to sleep, because if we are sleeping, let's say for 1 minute, someone can enter in a room and can exit in a room and we can miss that one. So in this particular case, we need to have a sensor always on. And that presents a really difficult challenges, because the sensor now needs to be very, very low power. The sensor, amplifier, and filter needs to fit in that range of 1.5 microamps that we were talking before. So now if someone enters in a room, what will happen? The sensor will detect that one and will send interrupt and will wake up microcontroller. So here I'm showing two different approaches. Sometimes when you need to have a sensor always on, the power requirements are much stringent compared to the applications when we are just measuring on a regular time base. So now I'm going to go to the HVAC, heating, ventilation, air conditioning system efficiency. And first thing that normally we forget is that the comfort level depends on two factors. It's not only temperature, because all our thermostat and the comfort in the house, we always relate to the temperature. We rise the temperature, we lower the temperature when we are trying to feel more comfortable. But there is another variable here, which is relative humidity. So the comfort level is combination of temperature and relative humidity. Also, to accept indoor air quality, there is a minimum airflow per person that needs to be maintained. We have normally air conditioning in a conference rooms, and if we have two people in the conference room and air conditioning is running one speed, we are feeling comfortable. Then more people enter in the same conference room, the air starts to be very uncomfortable because the air speed did not change based on how many people are in that room. So it's very important, to know how many people are, for example, in a room, so that we can anticipate how much air we need, instead of waiting that the temperature of the air goes up and then we retroactively act and start cooling. We want proactively to know how many people are in the room to anticipate requirements for the airflow and for the temperature. So having temperature and relative humidity and airflow also in combination with that will have to run HVAC system efficiently while keeping comfort level very high. So here we can see that on the left side there is a zone, temperature normally where we are feeling very comfortable. We are feeling from 68 to 82. That's our comfort zone. And also that the humidity can go from 30% to maybe 80%. Now, we also have two different requirements, depends on the winter and the summer. In the winter, our comfort zone will be lower temperature, when in the summer we need to have a little higher temperature. So for that application, we specifically design TI design. You can see on the bottom right corner, TIDA 00374, and that is humidity sensor that has a 2% accuracy, and there is also temperature sensor with 2% accuracy, and it can operate from the single coin cell battery CR2032 for 10 years, and it's an interrupt driven, as I said. So if you would like to see how it operates, how we achieve 10 years of the battery life, measuring relative humidity and temperature and transmitting that one please go on ti.com and search for this TI design. So what is also important, why that is important? This is very important because you can see now we have two different zones here, and we need to know what is temperature, what is humidity in zone 1. For example, you can see T-stat, thermostat, zone 1, and then we have also thermostat in zone 2. Now, the real requirements are that in zone 1, we have only 2 people, and we will need around maximum 40 cubic feet per minute of the air to dump in that area, because per person we need to provide around 15 to 20 cubic feet per minute of the air, that is coming in the room. Now, on the right side, we have 5 people, so requirements for the air there is around 100 cubic feet per minute, to provide. So why that is important? That is important because there is another thing that I will suggest you to take a look, and that's people counting. And so we can now have, there is a TI Design 750. This is using 3D of light camera, and it will detect how many people are in a room without violating privacy. Because yes, someone can say, why we don't just use the cameras? We can put cameras everywhere, but then there is a problem, because in the cameras we can see the people. We really violate the privacy when with this design we just count how many people are. They are blurred. We can detect the people, but we cannot see their faces. And so I will suggest you to take a look this design, which will provide now the information of how many people are in the room, and then we'll adjust how much air and the temperature of the air that we are going to provide for that particular room. So that's another way to make a very comfortable environment. You can see here that there is RICO board. The TI Design is connected to that board. There is USB 2, and then we have also Opto 8241 EVM connected there. So these are the results. This is the picture of the people in the room, conference room with the 6 people. You can see them around smiling. And then using our TI Design, you can see that we can detect the shape of the people, but we cannot see their faces and we cannot recognize them. So it is very important, again, I'm repeating that one for the privacy perspective, that every room can know how many people are there, but not more than that informations are provided. So now I would like to talk a little about preventive maintenance and predictive maintenance. So, normally, we can say if it's not broken, don't fix it. And that's correct. I'm first one saying that one. If it's working, don't touch it. It's working perfectly. But then what will happen actually is that it can break at the moment that I really don't want that it break. When I need that equipment, to work, it can break. So for that reason, it's very important that we know the health of machine, of equipment, and so before major defects are developed, and then we can schedule and do maintenance and replacement on certain parts on our terms, not when it's breaking or machine is not working anymore. So, we need to measure certain data, we need to analyze the trend, we can diagnose the problems from that trend, these trends, and then we can anticipate malfunction and do the preventive maintenance. So, for example, motor drive. Motor drives are used everywhere. They are used in, buildings as elevators, escalators. They're used for HVAC to pump the air and make us feel comfortable in the working place as at homes. They're used in factories for manufacturing and so on and so on. So what can happen? What can go wrong with the motor? Motors are relatively robust, but they run 24/7, they run constantly, they turn on, turn off, there is a lot of stress on them, and doesn't matter how good materials we use there, at the end, these materials are going to wear, and we are going to have a problem. We can have some problems. So first thing that can happen is that we can have shorted rotor bars, for example. Then most commonly is the damaged bearings, because motor is constantly turning around and there is a lot of stress on the bearings. So we can have oil whirl and wipe in the bearings, so that's another problem. What can happen is that during operation we can kick the motor, something can happen, and we can unbalance motor. We can bend the shaft, something like that, or misalign it just by installation, or during operation the supports can loosen, and so the shaft can bend because it's not aligned anymore. Then the stator lamination can be loosened. Also another problem is that overall support for the motor can be loosened, and also some other mechanical problems around that. Why that happens? It happens because, again, motors are turning around 3,000 RPMs. As well as they're balanced, they always vibrate. There are some additional machinery that is attached to that one, torque steps, load changes, all that will be a source of one of these failures or multiple failures. So what we do here, there is a TI design that will, for example, measure motor vibrations. And so now, based on motor vibrations, we can detect the health of motor very accurately, because we can look the spectrum, FFT, basically of this vibration, and on a certain frequencies, as the frequencies start changing, as we are doing these measurements in real time, we can see over the period of the time, for example, over a period of 6 months, 3 months, 6 months, or a year, how these frequencies are changing, and we can now predict what's going to happen to the motor and what needs to be changed before the motor breaks. So how this TI design is done using a piezo vibrating sensor, and that one is amplified and filtered. So from the sensor, we are going to analog front end and MCU for FFT. We are going to take the signals from the amplifier through the ADC to digitalize that one using reference voltage, and then in MCU, we are going to process that FFT. So now, on the right side, we have a wireless node with the power management. We can have energy harvesting. Now, this will be a good place to put a vibration energy harvesting that is using another piezo effect, for example, that we can now harvest that one. And then we are going to use the energy from the battery to provide it to the analog front end and the sensor. The CPU and RF core will take data, FFT data from analog front end MCU, and will transmit through the wireless signal. Another example of the preventive maintenance is typical HVAC system that everyone has in a house. So what we have here, we have a blower, we have a heater, and we have a cooling coil. Most commonly what will happen is that we will have a dirty coil. So dirty coil, sometimes we forget to change the filter, which is next to the blower. More dust will enter. Over the time, it's going to pile on a cooling coil, and once when the cooling coil is dirty, the airflow will not have enough airflow, and so the coil will freeze, and whole system will not work properly. So basically, solution for that one is another TI design that we are doing, where we have airflow sensor attached to the bottom of the coil, so we can see how much air is coming, because if the coil is working properly, enough air will pass through that opening, and we can detect that one. We can measure, it's measured from the air velocity that is going into the coil fans. Then we will have a temperature sensor above the coil, and so basically once when the coil is frozen or when it's dirty, this temperature will start going down. Why the temperature goes down? Because as more and more restriction we have in the coil, this slower and slower air will go through the coil, and more the air will cool. So basically on the temperature sensor, we can immediately see how coil is operating, and if the temperature is too low, we know that the coil is dirty, and we know that you know, something needs to be done. So before it freezes. So instead of having at once our coil being frozen and not having cold air in the house, we can now prevent that one, and we can schedule when we see the temperature from the temperature sensor and air sensor that the coil is starting to be dirty. We can schedule when we want to clean the coil and prevent very costly system repairs, you know, that can occur later. Here we can talk about, for example, temperature measurements in the motor control, non-contact temperature measurements. So this is another preventive maintenance that is going to minimize unplanned downtime, because with the early warning signals we can know that there is some kind of the problem in the machine. We are suggesting here there is a TMP007, and that is our infrared temperature sensor that basically can be installed on the PCB, and we can measure from both sides. So we can measure the air temperature or ambient temperature, and we can measure also temperature of rotating objects. So here we can see that we can measure, for example, temperature of the shaft or temperature of the rotor, which without non-contact measurements or infrared measurements will be impossible. So this is also going into preventing maintenance category. Another thing that I would like to show you here is air quality index, which again, air quality, you know, if our air quality is good, if the filters are good, if they don't have enough pollution, then our coils are going to be good in a cooling system and heating system. If there is too much of the particle pollution, then what will happen is that our system can be very easily clogged and will not operate properly. So let's talk first about air quality index. Air quality index, you know, there are different bases for the air quality system. Normally good is 0 to 50, and you know, unhealthy is 150 to 200. So it's very important to know, you know, what is the air quality index, and to know that one we need to know how many particles we have, 2.5 micron or 10. We call them PM 2.5 or PM 10. So you can see here small particles, you know, on the left side, PM 2.5, that's 2.5 micrometers and smaller, and they're very small. They're, you know, you can compare here to the human hair. You know, you can see the dust, basically the dust, pollen, mold that enters in a region of the PM 10 micrometers particles in diameter. You can see on the left side, like fine sand, beach sand is at 10 micrometers, 90 micrometers, almost 100 micrometers, you know, size. So this is just giving you an idea how big these particles are. So what we did a TI design, you can see it in the middle, where we designed the analog front-end circuit that is going to detect these particles. And on the right side, you can see the chamber where we have a LED diode, red LED diode in this case, transmitting the light, and then on the bottom right corner, we have a receiver, optical detector that is going to receive the scatter light. So how this is measured, it's measured that the dust will pass through this chamber. As dust is passing, it's reflecting the LED diode light, and then optical detector will detect that one, and we can now detect what is happening there. So here is our TI design that we did, and we use OPA 2320. Also, you can use OPA 2322. So there is a light source, there is a photo receiver. We are receiving the signals. We are amplifying with INA 132. All these parts are from TI, and then again we are filtering and processing that. So once when we go, our voltage when it go to A to D converter, then on the right side you can see what is happening. We can see these spikes in ADC code over time. And so now, not only that we can detect very specific particle, because P1, for example, can be threshold for 2.5 size particles, and P3 can be threshold for 10 micrometers particles. But because we have now ADC code, we are not going to fix comparator, we can detect the frequency, and we can also detect between. So we can have possibility not only to detect two major particles, but also a type of the particles, but also to detect the particles between. So how we go there? First thing, we need to go to ti.com. We will go to building optimization. You can see that one. You know, we are going to application and design, and under industrial, there is a building optimization. And so under that one, there is, once when you click on that one, you can see different areas that we are focusing here. One is fire safety, HVAC, security, and video surveillance. Then there is a tab with the reference designs. And so once when you go on that tab of the reference designs, then you will see some of our reference designs immediately. For example, humidity and temperature sensor, PIR motion detector. We will talk about all that before. And you can go there and look how they are done. What is, we provide with all documentation, schematics, Gerber, software, and so on. And so you can download that one, and we also have a board somewhere available. So that will be all for now. Now, if we have some questions, we can go with that.